Okay, we are on some chapter with a 7 in it, I think. So we're on chapter 7, and towards the end of last time, we started getting into stoichiometry and sort of putting together two things that we were talking about, which was one thing was converting grams to moles, which is using our molar mass to do so. And then we also talked about balancing equations. We also talked about types of reactions as well. But kind of putting both of those together is what's referred to as stoichiometry. And that's where we could do some calculations from the actual equations. And a lot of times, what we're trying to figure out is, for example, how much product we would make in a particular reaction if we know how much we're starting with in terms of our reactants. We may also want to know in a particular reaction if we produced a certain amount of products, how much reactants maybe we started with. And stoichiometry provides sort of a relationship to do those type of calculations. And as I mentioned last time, it's really nothing more than sort of a conversion factor that we use. Instead of sort of looking up the conversion factor in a table, we use the actual balanced equation as sort of a conversion factor to do these calculations. And that is typically because you're usually given information about somebody in that equation that you're not interested in. So you need a way to go from whoever you're not interested in to who you are interested in the equation. So, for example, if we had something like this equation here, we can use this balanced equation. And remember that stoichiometry calculations really do not work unless the equation is balanced. So that's always like the first thing that you definitely want to make sure. But we could say that using the coefficients here, we could come up with some relationships for this particular equation. We could say for every 1 mole of N2 we put in there, we get 3 moles of H2 out. And once again, they are equal to each other like an equality, but they're not equal to each other in terms of obviously the numbers don't equal each other. I think we talked about last time is sort of proportion wise of what you need to kind of toss into that equation to sort of get it to work right. We could also say for every 1 mole of N2 we put in there, we get out 2 moles of NH3. And we could also say that for every 3 moles of H2 we put in there, we get out 2 moles of NH3 as well. So these are equalities, which means from this one equation, we really have several different types of conversion factors. We could say 1 mole of N2 over 3 moles of H2. We could do it the opposite way, 3 moles of H2 over 1 mole of N2. For the second one there, we could say 1 mole of N2 over 2 moles of NH3, or 2 moles of NH3 over 1 mole of N2. Lastly, for that third equality there, we could say 3 moles of H2 over 2 moles of NH3, or 2 moles of NH3 over 3 moles of H2. So again, from this one sort of equation, we have basically 6 different conversion factors that we could use. We will not use all of them in a problem. We would just use whichever one that we wanted. And when we do stoichiometry problems, there's really sort of 4 basic steps that we follow. The first step is always this, which is make sure that the equation is balanced. The second step is to take whatever they give you and convert to moles. So in this case, let's just say that we did produce 13.5 grams of NH3, and we want to know again how many grams of H2 would we have started with. So in this reaction, the second thing that we'd want to do is convert our grams of NH3 into moles of NH3. So that is our really second step here. Remember to do that, like we've talked about, it is the molar mass from the periodic table to do that. So we would get the molar mass of NH3 in this case, which would be 1401 for our nitrogen, plus 3 times 1.008 for our hydrogen. And that's going to give us 1703. So we're going to use our molar mass here as a conversion factor. So we'll take our 13.5 grams of NH3 using the molar mass that we just calculated, grams on the bottom so they cancel, moles of NH3. And that will get us here 13.5 divided by 1703. This made up example 0.792718 moles of NH3. I'm not going to round too much at this point. The problem again is, and this is really what the stoichiometry is about, we have NH3, but we ultimately want to get to H2. So we need a way to do that conversion, and it is from the equation that we could do that. So we would first go to the equation and find the relationship there, and that's between NH3 and H2, which would be this guy here. This gives us, again, two conversion factors that we could use. Again, the goal here is to get rid of the NH3. So NH3 is up on top. So we would want to use this conversion factor here. And that is the big stoichiometry step. That's what's going to get us from NH3 to H2 in this case. And if we do that, which is our third step, which is sort of use the mole to mole relationship, we will take our conversion factor, 2 moles of NH3 for 3 moles of H2. And that is the big stoichiometry step right there. The moles of NH3 are going to cancel. So we're going to times it by 3 and then divide by 2. And that's going to give us something like 1.189, we'll call it 08 moles of H2. Now, at this point, if you did want the answer in moles, you would be done. You should clean up the sig figs, obviously. But in this case, we don't want the answer in moles. We do want it in grams. So this does require us to do really the fourth step, which is to take our units of moles to some other unit. And in this case, we are looking for grams. So we will need the molar mass, but we do have to remember at this point that we're no longer at NH3 in this example. We have transitioned over to H2, so we would need the molar mass of H2 from the periodic table, and that is 2 times 1.008. And it's going to give us 2.016, I believe. And lastly, here we'll do the fourth step, putting our grams up on top since that is where we want to end with it. And that will get us something like 2.40 grams of H2 in this particular case. So all these sort of stoichiometry problems for us in this class are pretty much these 4 steps. Balance the equation, take whatever they gave you, get it to grams, and then go from grams to moles. Then use the equation as a conversion factor to use the mole-to-mole relationship, which once again is nothing more than just the coefficients. And then the last step here is a lot of times you will take those moles and convert it to some other unit. In this case, grams. You could do any other unit you want. But those are really the 4 basic steps. Any questions on that one? I think we also talked about at the very end last time, a reminder that, again, sometimes people think when they do stoichiometry problems, they do have to sort of go across the arrow. As I might have mentioned at the very end last time, you could do a stoichiometry step between 2 reactants. I could do a stoichiometry calculation between 2 products. You could go from products to reactants like we just did here. You could go from reactants to products as you did, as we can do as well. So you can really use these type of calculations for really anybody in that equation, as long as you know really one piece of information about somebody. Yeah.
Let's say the ask us like right now, in addition to R, so how much do we put of nitrogen? Solve it as 13.6 minus 2.4.
If you want to know how much nitrogen, is that your question? So actually, you could do one of 2 things. You could either do the calculation again at the very beginning. and start with the 13.5. And then instead of doing the relationship between NH3 and H2, you could do it between NH3 and N2. The other thing you could do, which is what's nice about stoichiometry, is we actually do have the answer, say, right here. We have our moles of H2, right? Or you have your moles of NH3. You could then do it from the H2 moles, from H2 moles to N2. So for example, if I get rid of, let's see here. So let's get rid of this part here. So for example, it's asked at the end, they're like, also want to know about N2. So we could actually, if you want to, pick it up in a couple places. You can pick it up here and then go to N2. You can pick it up here as well and go from N2. So if I did it from here at the 1.18908 moles of H2, I would then need the relationship between these two guys, right? And those two guys is right here. And in this case, I would need to use the conversion factor on the left here, right, to get rid of my H2. And you could do the exact same thing. You would do the 3 moles of H2, the 1 mole of N2, and that would give you moles of N2. If you wanted grams, you then could do the molar mass of N2, right, which would be 2 times 14.01 grams of N2. So you could actually pick it up in 2 places. You could either go from the back to the beginning and kind of do it, to that one. If you have the moles along the way, you could do it as well. So they all come out the same. It will not, because 13.5 is how much you produced, I think. Yeah, so so you're asking, will the end result be the total of what you produce? Yeah. So it will probably be pretty close to it. It might be slightly off, but with some rounding and stuff. But there is that conservation of mass along the way. So you would probably have about that many grams that you would need to produce that many grams. Yeah. Other questions? But if you want to know the moles or just individually know, you could do a separate calculation as well. Or pick it up anywhere along the way, because that is sort of the relationship that you could have with the stoichiometry. But yeah, since we do have obviously the same mass on each side, you'll end up with, in this case, 11 point something, I think, as we did now. Other questions? The other important thing we talked about as well is in terms of molar mass. When you're calculating molar mass, remember that you do it just for the formula by itself. So regardless of the coefficient, you should just calculate the molar mass based on just the formula. Don't include the coefficient, because we include the coefficient, when we do our stoichiometry part of the calculation. All right, so let's take a look at some here. Lithium metal reacts with water to form hydrogen gas and lithium hydroxide. How many moles of hydrogen can be formed if we react 5.32 moles of lithium? And the answer to your question is because we also only had one product in that case, right? That's why it added up to 13.5. Right. So again, follow the 4 steps here, which again is balance the equation, convert to moles, mole to mole relationship, and moles to some other unit if necessary. Okay, let's take a look and see how you're doing. So in this case, we want a balanced equation. It's not given to us, it's given to us in words. So remember that as we talked about, when we talked about sort of writing equations, you want to make sure that you get the right formulas first, and then you should balance it. So again, try not to do both of those things at once. Lithium metal is just Li, right? No charge, just a piece of metal. Reacts with water, which is H2O. To form means you have an arrow. What are we forming there? Hydrogen gas, right? Hydrogen gas is a diatomic molecule, which means it should be H2 and not just H. So that's really important. And lithium hydroxide, lithium is group 1, hydroxide is -1, which means we have something like that when we put it together correctly. So that should be your unbalanced equation at this point. You then need to balance it and make sure everything is balanced here. And in this case, I think maybe like a 2 there, a 2 there, and maybe a 2 there. I'm just putting 2, so for the best here. I got 2 lithiums, 4 hydrogens, and 2 oxygens. So I think we are good in this case. Any questions on that there? So that is step number 1. Really, the only thing given to us is we have 5.32 moles of this guy, and we want to know how many moles of this guy, H2, that we're going to end up with. Do I need to do number 2? I don't, because it's already done for me. So don't go backwards. It's already in moles. So just put a check and move on. The next thing means that we now want to find really the 2 things we're interested in. One thing would obviously be what they gave us, which in this case is the lithium. The other thing that we're interested in is what we're trying to find, which is H2. So we're really interested in these 2 guys here. Once again, the stoichiometry here means that there are 2 moles of lithium for every 1 mole of H2. And once again, that is nothing more than the actual coefficients from the balanced equation. That's going to give us 2 possible conversion factors to use here. So now we could actually do step number 3 here. We'll take what they gave us, which was 5.32 moles of lithium. Remember, we want to get rid of lithium, which means we need to put it on the bottom. So we are going to use a conversion factor here. That will give us 1 mole of hydrogen up on top, 2 moles of lithium on the bottom. This is the big stoichiometry part where the lithium will cancel each other out. And we will end up with 2.66 moles of hydrogen. In this particular case, we do not need to do step number 4 because that is what we're looking for, right? We're looking for moles, so we are good. Obviously, if we were looking for grams at this point, we would need the molar mass of H2, and we could figure out how many grams that would be in this particular case. This is what is sometimes referred to as the theoretical yield. It's basically how much you would produce in that reaction if everything went perfect, no side reactions happened or anything like that. Any questions on that one there? All right, so let's try another one here. That's one we just did. Let's try this one using the same equation, same reaction. We now want to know how many grams of hydrogen would we produce. Hydrogen is 1.008 and lithium is 6.941. All right, once again, follow those 4 steps. Balance the equation, convert to moles, mole to mole relationship. Okay, let's take a look and see. So again, trust me when I tell you, just follow these 4 steps and you should get to the answer, hopefully. In this case, we're starting with grams here of lithium, 81.75 grams. And we want to know how many grams here of our hydrogen we're going to get to. So first things first, we want a balanced equation, which obviously was done in the previous part of the problem. So we're good to go. Number 2, you want to convert to moles. And in this case, we have 81.75 grams of lithium. That means we do need to do that. So we would go to the periodic table and find lithium's molar mass, which is right there. And we would use that to convert it into moles. Our grams of lithium will cancel, and that will give us 81.75 divided by 6.941. Going to get us about 11.8, or actually 1178 moles of lithium. In this case, we're not interested in lithium, right? So we're interested in hydrogen. So that is where the stoichiometry part comes into play. We're going to go again to our equation and find lithium. And we're going to find hydrogen, which again are the two things we're interested in. And that relationship, as we saw, is our mole to mole relationship. And it's the same one we used in the previous part of the problem, which is 2 moles of lithium gives us 1 mole of hydrogen. And that means we could continue on with 11.78 moles of lithium. We're going to use this as a conversion factor. And again, opposites to cancel, which means the moles of lithium need to go on the bottom, the 1 mole of hydrogen up on top. And we will end up with here about 5.88, I'll call it 9 moles of hydrogen. So that takes us through here and here. The last thing here, which is convert our moles into some other unit, which, as we talked about last time, you should definitely be in moles at this point. If you're not, then definitely something went wrong. We do need to do that, but we do need, again, here the molar mass of H2. So we would go back to the periodic table to get our molar mass of H2. Which should give us a 2.016 grams per mole. Taking our 5.889 moles of H2, using our molar mass here. Grams are actually going to go on top, so we end up with grams. Moles will cancel, and that will end up with here, called 1187, looks like. 11.87 grams of H2 in this case. Again, 4 steps, follow them, yes. You do not. So again, whenever you calculate molar mass, if that's what you're asking, where we did like the 6.941 grams per mole, you should always do it based on the formula, because that's really what the definition of molar mass is how many grams there is in 1 mole of something. And 1 mole of something basically is represented by just the formula by itself. So you don't want to do that, because although you'll get the same answer, perhaps if you did it correctly, but oftentimes what people will do is they shouldn't do that, because that's not really what the molar mass is. But if they do it there, then they will also do the stoichiometry part, and before you know it, you did that twice in this example, and you'll be off in terms of the answer. So always molar mass, regardless of what the coefficient is in the equation, should be calculated just based on, if you just took one of the formulas by itself, that's what it should be. Other questions? All right, let's try maybe some more here. Just make sure. All right, so we got this equation here. If we started with 765 grams of C6H12O6, how many grams of CO2, we'll go with grams there, of CO2 would we produce? So carbon is 12.01. All right, let's take a look. So again, even though this equation may look scarier, a lot more stuff, bigger numbers, doesn't matter. Still same 4 steps. I see numbers and coefficients there, so I'm going to assume it's balanced. You should check it. I would think in most cases it probably will be balanced, but you should double check. And if you do, you'll see that it is balanced. We do have grams of this guy here. We're looking for grams of this guy. And that means that for step number 2, we do need to do the convert to grams, whatever they gave us. I'm sorry, convert to moles. whatever they gave us. And in this case, it would be our 765 grams of C6H12O6. Once again, we do need to go to the periodic table and get the molar mass of this guy. And that would be 6 times our 12.01 plus our 12 times our 1.008. And we got 6 times 16 in this case. It's like 180.2 grams per mole, I believe. And we're going to use that as a conversion factor here to convert our grams into moles. So we're going to go with our grams on the bottom, which would be 180.2 grams per mole of C6H12O6. If you want to get an answer at this point, you can. You could actually just continue on with the calculation, but I'll get an answer here if you want to here. And it looks like 765 divided by 180.2 is going to give us 4.24528 moles here. I'm not going to round too much because it's not my final answer. At this point, we've now converted it to moles. And we did that so we could do step number 3, which is our mole to mole relationship. And that means we're going to go to the equation, find the 2 things we're interested in. One thing is what they gave us. The other thing is what we're trying to find. And we can see, again, from the coefficients, for every 1 mole of our glucose here that we throw in there, we will get 6 moles of our CO2. That, again, is the stoichiometry part. That's what's going to allow us to go from the C6H12O6 to the CO2. We're just going to simply use it as a conversion factor. So we'll take our number that we got there previously. Once again, we want to go opposites to cancel, which means 1 mole C6H12O6 will go on the bottom. 6 moles of our CO2 will go up on top. The moles will cancel. And again, that is the big stoichiometry part there. And that's going to give us something like 25.471, we'll call it 7 moles of CO2. Again, if I wanted the answer in moles, I would technically be done at this point. But once again, here we are actually looking for grams. So we do have to do the 4th step, which is take our moles now and convert them into grams. And that's, again, going to require a molar mass. But in this case, we do need the molar mass of our CO2, as that is where we're at. That gives us 12.01 for our carbon from the periodic table, plus 2 times 16 for the oxygens from the periodic table. Little 4401 action there, grams per mole. That means here, to finish it up, we would have our 25.4717 moles of CO2. Use our molar mass as a conversion factor. We do want the grams up on top so that we do end up with grams. We do want the moles on the bottom so that the moles cancel. And that is going to get us here about 1,120 grams of CO2 in this case. Yeah. Little 3 significant figures really based off of the only number in the problem, which is the 3 that we started with in this case. Yeah. Otherwise, you got like 1121, I think, on your calculator, something like that. Question on those 4 steps. Now, I did it in each of these 4 steps, and I did get an answer after each step. Again, just to kind of show you the steps. But absolutely, you could just go from one part of the calculation to the next. You could go from here to here to here and not get an answer sort of in between. And that's perfectly fine as well, as long as you have it set up that way. Any questions on that one? Questions? No? Okay. All right, let's try one more here, I think, to finish up this chapter. How many grams of cisplatin, whose molar mass is 300.1 grams per mole, can be obtained from 0.7752 grams of K2PtCl4? Molar mass from the periodic table there, 415.1. So see what you come up with in this case. What's that? It's a long one, but it's still the same 4 steps, even though it may look scary. Okay, so let's take a look again. We're going to follow the same 4 steps. I see an equation, some coefficients. So I'm hoping that's balanced. I'm just going to hope for the best on that one, but it is balanced, I hope, if you check it out. In this case, we are starting with 0.7752 grams of this guy. And we want to know how many grams of that guy there that we're going to produce. They did give us some other numbers. These obviously are the molar masses, so you don't have to go to the periodic table to calculate it yourself. If it wasn't given to you, then you would need to go obviously to the periodic table and use the formulas and calculate both of these numbers from the periodic table. So again, those are the molar masses from the periodic table that they were nice enough to give us. So second step is to convert to moles, which again, we do need to do. So we'll take our 0.7752 grams of this guy here. And we're going to use the provided molar mass because they were nice enough to give it to us there. And that's going to be the grams are going to go on the bottom. The moles here will go up on top. And again, you can continue on the calculation, or if you get an answer here at this point, you would have something like this, I think, 0.001868 moles of K2 PtCl4. Once again, we're not really interested in that. We are interested in our product. So this is, again, the stoichiometry part where we're going to look at the relationship between the coefficients of those two from our balanced equation. And we see in terms of our mole to mole relationship, for every 1 mole of our reactant there, we will actually get 1 mole of our product, which makes it a pretty easy relationship in that case, even though there's a lot of letters. There you go. So we'll take our number 0.001868 moles of the K2 PtCl4. We want to get rid of that, so that's going to go on the bottom here. What we're interested in will go up on top. And I think I could do the math there. We're still got the same number at this point. But we have converted it now into our product here, which is what we are interested in. At this point, we are not interested in the moles. If we were, we would be done. Again, we are interested in the grams. So we do need the molar mass of that, which they were, again, also nice enough to provide for us. Otherwise, again, you would have to go to the periodic table to do so. So step number 4, we're going to use our PtNH3 2Cl2, which has a molar mass from the periodic table of 300.1. That's going to be, again, a conversion factor here to convert our moles into grams here. Again, we do want the moles on the bottom. We want the grams up on top. The moles will cancel, and that will get us there about 0.560. 0.560, and we'll go one more, 4 grams of PT NH3 2Cl2 in this case. Again, the same 4 steps as you can see. Hopefully you're seeing a pattern that it is just the same 4 steps. Just follow the steps. If something's done for you, just go forward, don't go backwards, and it should again lead you to the right step. Any questions on stoichiometry or how to do those type of problems? Yeah. No, so again, you do need to show the work. So you don't necessarily have to list the steps unless it helps you, then you could do that. At minimum, you need to have like, if you're going to want to do it all, maybe in one calculation or so, you do need to have basically this to here to here. Yeah. So basically that part of it needs to be shown for credit. Yeah. But if it helps you to do all the rest of it, do all the rest of it. Don't really matter. But that's basically what you need to show is those steps. Yeah. Other questions? Okay. All right. So that should wrap up this chapter. Believe it or not, chapter 7 in the books, they say halfway there. Yeah. halfway to somewhere. I'm not really sure where we're halfway to. But all right. Okay, we're going to get going here on chapter 8, which is about gases. So they're going to talk about a number of different gas laws throughout this chapter. We got a few more to go before we get to organic. So a few more chapters of calculations before there is no more calculations. So chapter 8 here is gases. Obviously, we're going to be talking about the state of matter that's in the gas state. And in the gas state, as we talked about previously, that's where we find molecules and stuff flying around. As they're flying around, there's a lot of collisions that could occur. As the number of collisions occur as they're flying around, we associate that with an increase in pressure. Less collisions, we usually see sort of a lower pressure sort of happening. They obviously have a lot of energy, otherwise they wouldn't be flying around. So let's talk about some substances that exist as gases under sort of normal pressures and temperatures. When we talk about sort of normal pressures and temperatures, sort of like room temperature type conditions, that usually refers to 1 atmosphere, which is what the ATM stands for here. That is a very common unit of pressure and atmosphere. And sort of normal, sort of everyday sort of temperatures considered 25 degrees Celsius. And under those sort of normal conditions, ionic compounds, which are metals and nonmetals together, that are held together by really strong electrostatic attraction between the positive ion and the negative ion, will not exist as gases under those type of conditions. To overcome that really strong attraction force between the positive ion and the negative ion would require a lot of energy, which typically doesn't happen under normal conditions. You can essentially heat the heck out of an ionic compound, and it probably will start to melt before it will go into the gas phase. So it takes an enormous amount of energy to basically rip those guys apart. That's probably one of the strongest sort of attractions you could have, is that kind of electrostatic attraction between the positive and negative guy. Now, covalent compounds or molecular compounds are a little bit different than ionic compounds. There's a lot of molecular compounds, these are the guys that are basically held together by sharing of electrons. Things like carbon monoxide, carbon dioxide, hydrogen gas, ammonia, and methane, which stuff comes out of the gas here when you light your Bunsen burner. These are all gases at room temperature, but a lot of molecular compounds are actually liquids and solids at room temperature. The main difference is a molecular compound can easily, a lot easier, I guess is the way to say that, be converted into the gas phase than, say, an ionic compound. And that is because, for example, we look at something like water, which is a very common example of this. We look at something like water. Water is a polar molecule, like we talked about with bonding. And it has a positive side and a negative side. Positive side, the hydrogens, the negative side, the oxygens. So when two water molecules, for example, come together, they're held together by the hydrogen is positive and the oxygen is negative. This is what is referred to as hydrogen bonding. And hydrogen bonding is a strong intermolecular force. And an intermolecular force is the force that holds one molecule together with another. One of them same, different molecules. Basically, two molecules basically interact with each other and sort of bond to one another and are held together. And that means that when we take something like water and we start to heat it up, the bond that actually breaks is this bond between the different water molecules. And what happens is that allows this water molecule and this water molecule basically to go into the gas phase and create steam. It's what happens when you boil water, right? And it starts to boil at the boiling point. You get steam coming out, right? When you're making pasta, right? And you guys saw things starting to boil, you're breaking the bonds between different water molecules. For example, if we look at water, just one water molecule, the covalent bonds where they're sharing electrons, these are what are known as intramolecular forces. And those are forces within a actual one molecule. So the actual sharing of electrons there between the oxygen and hydrogen on one side and the oxygen and hydrogen on the other side. That's what's known as an intramolecular force. And intramolecular forces are always much stronger than an intermolecular force. And we know that from the water example and maybe boiling water to make pasta, right? When we boil water, we end up with steam and a boiling, which is water molecules. We do not end up with hydrogen gas or oxygen gas, which would not end well probably for making the pasta. It doesn't break apart. So as we heat it, we do not break these bonds in individual water molecules. We instead break the bond between different water molecules, which are intermolecular forces, and that allows them to basically be free. So intermolecular forces are always the weaker of the two between that and intramolecular forces. And there's different levels of intermolecular forces. Something like water actually is a relatively strong intermolecular force. Something like methane, for example, this guy, he's actually a nonpolar molecule. And he would use something that's known as dispersion forces, which are the weakest type of intermolecular force you could have. And pretty much, if you look at it, they're not going to stay together. They're just going to kind of break apart, essentially. And that's why a lot of things like methane, as we'll talk about when we get into organic, these are things you probably heard of: methane, propane, butane. Those are all gases, right? And flammable gases. They're all nonpolar. They're all held together by these really weak forces, which they're very easily go into the gas phase. That's why a lot of organic molecules as well. And when you do some of the organic labs, they will throw you in the fume hood, not you personally, but you will do the work inside the fume hood. And that's because a lot of organic molecules are very what they're called volatile, which means although they're in the liquid phase, they can very easily just go into the gas phase just from sitting there because they're not held together by really strong forces. And then a lot of them are also flammable, which is not good if it goes into the gas phase and you got like a Bunsen burner going, right? So it's gonna catch on fire. So a lot of times when people work with organic compounds, they oftentimes will do it inside the fume hood, because of that, and also a lot of them smell as well, not so great because they are volatile and they go into the gas phase really, really easily. So the general rule is the stronger the intermolecular force, the stronger the force it holds one molecule together with itself, the less likely you will find it in the gas phase under normal conditions. The weaker that force it holds those guys together, like methane, propane, butane, the more likely you're going to find those things as gases under normal conditions. So some other substances we find as gases under normal conditions, a lot of those diatomic molecules, which are elements that we talked about: hydrogen, nitrogen, oxygen. Those are all those H2O2, N2. Fluorine and chlorine, F2 and Cl2. Ozone is a gas that's three oxygens together. Good in some places, not so good in other places as well. Group 8, right on the periodic table, which is our noble gases. Those are also referred to as being monoatomic, which means they come as ones, basically, unlike hydrogen, oxygen, and nitrogen. That's all of our ons, our helium, our neon, argon, krypton, xenon, all the ons there in group 8 in terms of our gases. So these guys in kind of the bubbly area there are pretty much gases under normal conditions and how we sort of find them. Now, it is important to talk about distinction between a gas and a vapor. A gas is a substance that under normal conditions will be found in the gas phase. A vapor, on the other hand, is a substance that normally is found in the liquid phase or solid phase, but can be converted into a gas. Again, water is a prime example of that. We oftentimes call it water vapor rather than water gas because water is normally found in a liquid state, but we can convert it into a gas state. So there is a difference when we talk about something being a gas and a vapor. Plus, water gas doesn't sound so right either when you say water gas. So we oftentimes refer to it like that as water vapor or steam in a lot of cases. Now, a barometer, who was invented by Torricelli, there is a device is used to measure. The right pen there is used to measure pressure. Traditional barometers, which I haven't been up into your lab room in a while, but you might still have a traditional barometer up there. I'm not sure. A lot of schools have taken them out. It's usually a sort of bucket there, and a bucket is a nice description, I suppose, mercury, and usually like a glass tube in the mercury. And as the atmospheric pressure sort of exerts itself on the mercury in the tube rises, and you read the mercury off of this sort of glass tube. A lot of times schools have gotten rid of the barometers because they contain mercury and they use more of like an alcohol sort of barometer that's sometimes used. Some really important units of pressure there is an atmosphere, as I said before, which is an ATM. 1 torr is equal to 1 mmHg, and that is a millimeter of mercury, and that is because the barometer here was mercury. And on this scale here, you would read a ruler, and you would oftentimes read the ruler in inches, centimeters, and sometimes millimeters of mercury when you would sort of read the pressure unit there. So 1 atmosphere is equal to 760 millimeters mercury. That's equal to 760 torr. 760 is your magic number there to convert between those units. So if you have atmospheres and you want millimeters of mercury or torr, you're going to multiply by the 760, and that will give you your torr or millimeters of mercury, which is a 1-to-1 relationship. Or if you're starting with torr or millimeters of mercury, you will divide by the 760. And that will get you to atmospheres. So 760 is used a lot, again, as a conversion factor. And these are the 3, I would say, most common units of pressure that you'll come across probably in this class. There are other units of pressure like pounds per square inch, PSI. There are pascals and kilopascals. There's also bar as a unit of pressure, which is pretty close to an atmosphere. It's like 1.01 to 1. So there's a lot of different units, but I would say this would be the big 3. Torr, millimeters mercury, and atmosphere are usually the 3 units that you see the most here in our chemistry class and most chemistry classes that you take. Here's a much better reading drawing of the barometer there. I know if you close your eyes, my other one looks similar. Mercury is an interesting substance. It actually has a meniscus that goes the opposite way. It actually curves upwards. If you actually do read a mercury barometer, you actually read from the top of the meniscus in this case, because what happens is basically the attractive forces between mercury in itself versus mercury in the glass is actually stronger. So it actually comes in on itself and makes sort of a unusual meniscus. Most of the time we see meniscuses going in this direction, but mercury is sort of an exception. It actually will go in the opposite direction. So let's talk about some gas laws here. And the first one we're going to talk about is Boyles Law. And when we talk about gas laws, there's 3 variables we deal with: pressure, volume, and temperature. And in certain cases, we may keep one of these things constant and sort of vary the others. So in Boyles Law, he looked at the relationship between pressure and volume, and he kept temperature constant. So Boyle looked at this relationship between pressure and volume, keeping temperature constant. And what he saw was a couple of important relationships. He saw that as we lower the volume, that means that all my gas molecules are going to be really close to one another, right? And because they're really close to one another, we would expect a lot more collisions to occur, right? Everybody's going to be running into each other and the container as well. And because of that, we would expect the pressure actually to go up. So as the pressure goes up, we see that the volume actually goes down in Boyle's relationship because of that. And vice versa, in a situation where maybe we increase the volume, gives everybody a lot more room to sort of fly around in. And that means that the number of collisions that's going to happen is actually going to decrease. And what we will see is actually a drop in the pressure. So as the pressure goes down, we typically will see the volume go up. So sort of an opposite relationship: as one goes up, right, the other one goes down. And that is Boyle's law. And Boyle's law right here is P1 times V1 equals P2 times V2. The pressures here can be any unit of pressure you want, as long as they're the same on both sides. So they got to be the same on both sides. The volume here could be any unit of volume you want, as long as they are the same on both sides. So this is sort of like a before and after event. You basically change one thing, you change the pressure, change the volume, and you can see the relationship that occurs there. So P1 V1 equals P2 V2 is Boyles law. And here's a graph of Boyles law. You basically can see here at a lower volume, a much higher pressure, and at a larger volume, a much lower pressure basically happening in this relationship here. All right, so why don't we try one here? An inflated balloon has a volume of 0.55 liters. At 1 atmosphere, it goes to 6.5 kilometers, where the pressure is 0.4. What is the final volume, assuming temperature remains constant? So take a shot at there, see what you come. Okay, so since we're getting down, let's take a look at it. I would highly recommend as you go through these sort of gas law problems, it's really a good idea just to pull out the information and label them as to what they are. Are they pressures? Are they volumes? Are they temperatures? And a lot of times you'll be able to kind of see the gas law that you would need to use. So here we have obviously a volume that is 0.55 liters. It is 1 atmosphere, which is a pressure. The 6.5 kilometers is just useless information in this particular problem here. We have another pressure that is 0.4 atmospheres, and we are looking for a volume. Although we don't have a lot of gas laws to choose from, you should kind of see Boyle's law developing there as you sort of label everything. Doesn't matter which ones you make ones or twos, it really doesn't, as long as you kind of keep the information that goes together. Most of the time people will just do it the way it is written in the problem, just call the first ones ones and the other ones twos. In this case, we do want to check units. We have atmospheres on both of our pressures, so they're in the same unit. So we want P1 V1 equals P2 V2. In this case, we're looking for V2. By the way, when you go across the equal sign, everybody ends up in the opposite location, which means technically that is on top, which means when you take it across, it goes to the bottom, or basically dividing by P2 to the other side. That would give us P1 V1 over P2 is equal to V2. Now we can put our numbers in. P1 would be 1 atmosphere. V1 would be 0.55 liters divided by our P2. The atmospheres will cancel. That's going to leave us liters, which is good because we are looking for a volume. And in this case, we will end up with 1.4 liters, right? Question on that there. Now, we could also think about the relationship that we talked about. What we see in terms of the pressure is it started at 1 and went to 0.4. That means the pressure goes down. That means the volume should go up. So did it? It started at 0.55, ended at 1.4. So understanding the relationships is also really good, because you could make sure you didn't hopefully invert any numbers or anything like that, and hopefully make sure that it does make sense. Any questions on that?